Good morning, Mackenzie. Do you know why the homeschoolers are the first? Oh, the high schoolers. I don't know. I don't know, Daniel. All right, we'll go ahead and get started. I said 2 or 3 minutes, but it's 9:04. We can get started. People will join on. Before I start with anything new, I wanted to check in and see how everyone is doing with chapter 6 and see if anyone has any questions or sections they want to review again. 6.6 gave you loads of trouble, Elijah says, as the answers make no sense. Okay. Well, that's not cool. Is there a particular one, Elijah, that made no sense? Okay, so let's do some problems. So Mackenzie, I see you have 6.2 as well, so let's do that as well. All right, so let me get my book here. So 6.6. You don't know how to get the answers. Well, let's figure out how to get the answers, Elijah. 5, 7, or 9. And Elijah, sometimes it may be that how they have written their answer might look different than your answer, but might be the same. One of those sections. So if you have or have not done 6.6 yet, I kind of forgot to warn you that this is one of those sections. Okay. This is one of those sections where they could possibly simplify to a certain degree. You can come up with a slightly different looking answer that means the same thing. But Elijah's saying, no, that's not the case. All right, well, number 5 is actually, I don't know if you guys know this, if you figured it out by now, when they have that circle around it, should have it completely worked out in the back of your book in a different section. So let's do number 7 in 6.6. Okay, so we have, this is 6.6, and we have number 7. It is -2 square root of 4x plus equals -11. I never even know where the... Oh, okay. There is a page back there that has one section of the back of your book is answers, and the other one is worked out solutions. So the red section actually will have for you, but I'm happy to do it as well. All right, so let's go ahead and do number 7 because that one is not worked out. When we're solving these types of equations, we're trying to get x by itself, right? We're kind of back to our standard algebra. How do we solve equations? So we're trying to get x by itself. To do that, we got to get rid of all this other stuff that's happening. So right now it's being added by 13. It's being multiplied by -2, and it also has the square root 24 under the square root sign, right? So algebra problems in a while. We've been kind of moving on to higher math, right? But we're solving algebra problems is we kind of want to strip everything else away and get down to x. Now there's no formal way to do this, but it's kind of a learning how to do this. I like to think that usually when you're solving for x, that you're kind of doing reverse PEMDAS. Okay, you can, I could say, oh, I want to divide both sides by -2. I could do that, but it's going to make my life harder because then I have 13 divided by -2, and I don't really want to do that. So it's not always perfect to say that, but I think that kind of a starting place of doing reverse of PEMDAS is a good place to start when you're solving. So what I mean by that is, and when I'm trying to get x by itself, the first thing I want to do is get rid of the 13. And I didn't say forget PEMDAS. I said do the reverse of PEMDAS, right? So you want to do add MEP, sad MEP, when you're solving, right? You're kind of undoing PEMDAS. You still have to keep in your PEMDAS rules, though. It's not a perfect, perfect way to do it. Anyway, so you look at this equation, see it, the first thing I definitely want to do is I want to send 13 to the other side, because that's easy, right? It's just hanging out here plus 13 all by itself. So I want to subtract 13 from both sides. And I am left with -2 square root of 24x. I've gotten rid of my 13, that's good. And -11 plus -13 is going to give me -24. So now, okay, what do I do next? Still have the square root, I still have 24, and I have -2. So now I'm kind of going to get to the multiply, right? I want to kind of get rid of this -2. And to get rid of -2, I'm going to divide both sides by -2. Now, like I said, in this step, I could have divided by -2 first, but I'm still going to have that 13 over -2, and I don't want to deal with that. So -2 times the stuff on the square root divided by -2, that cancels each other out. And nice over here, 4 divided by -2, that not only divides evenly, but it cancels out my negatives, right? So this just leaves me with 12, and I'm left with 24x, and the square root sign equals 12. So now I'm down to square roots, which kind of goes under the E in PEMDAS, right? Because really square root is just to the 1/2 power. And times x. I can't divide out 24 like it is right now, but I can square both sides of my equation. Okay, so then I end up with anything square root squared is just itself. So I end up with 24x equals 12 squared, which is 144. And then I just need to do what? Divide both sides by 24. And I end up with x equals, evenly, let's think. Yeah, 6. All right, Elijah, what did you think of that one? Is that what the book said? I didn't even look. Yeah, number 7 is 6. All right. Well, that's good that we got the answer in the back of the book. Yeah, somehow I know. Well, now go back and kind of look. Do you want to see another one? Because I'm reading your little description. You said add 13 to 11, which is what we did first, Elijah. Divide by 2. Okay, so really, I mean, yeah, okay. Square, then divide by 24. So you actually had all the steps above. You had the steps right, so it must have been some little math error. Which is frustrating when you have the steps right and it's like one little thing. Oh, sorry. You sure you don't want to do one more? All right. Mackenzie had some questions about 6.2. So, Mackenzie, any particular one in 6.2? You just kind of want to see a general overview. 6.2 looks scary when you look at the homework. Got all kinds of radicals and crazy stuff. We never finished the notes for it? Oh, I didn't realize that. Well, I apologize. Let me pull up my notes. Let me pause my screen here and pull up. I'm sorry that we didn't finish that. My brain apparently was still on vacation. Okay, chapter 6. Okay, so I have the notes back up here. And I do remember we took a long time on the first section. So I think we did not quite get through there, right? Yes, and there were a lot of problems in this section, weren't there? Why don't we pick one out of maybe each section and kind of go over the rules for each one, and you guys can see if you're kind of tracking along. So we had problem 61. Go straight for the hard one, right? Okay, 1 through 39. So we have, let's do this. Let me zoom in a little bit and pull this up over here. We want to kind of keep this as our cheat sheet. We can do this. We can do the harder ones. Let's just start a little easier, right? No, that's not what I want to do. Now I want to copy that. No, I failed. All right, computer people. We want to leave this up here. And I want to have other places to write. So, yes. All right. So we want to maybe look at one of the problems that is in our book. So number 3 through number 13, I'm on page 424, 6.2. Number 3 through 14 say simplify, well, they all say simplify the expression, but all of these have to do with the product of powers. So when you multiply two numbers that have two expressions that have the same base and different exponents, then we go ahead and add them. Or a power of a power, which means if we have a to the m to the n, then we multiply the powers together. Or if we divide. Okay, so let's see. Number 7 looks a little bit tricky, so maybe let's look at number 7. Okay, so this is number 7 in 6.2. And Mackenzie, if you have a particular one too, let me know. So number 7 has 80 to the 1/4 power divided by 5 to the negative 1/4 power. Now, I should mention that some of these don't kind of go in a straight line. So the way I might have solved this might look different than the way you may have chose to solve this. Okay. So the first thing that you notice is that the exponents are the same, but the base is different. So we kind of have that going on. right? We got to figure out what to do about that. We also have a negative exponent in the denominator. So that's kind of another, what do we want to do about that exactly? So where I would probably start is I would, I think I would probably flip this negative exponent to the numerator first. Okay, so what I mean by that is because whenever you have a negative exponent, you can rewrite it as a positive exponent by flipping from either the denominator to the numerator, or if you have a negative exponent up in the numerator, you can flip it to the denominator. Okay, so I'm going to go ahead and rewrite this as 80 to the 1/4 power times 5 to the 1/4 power. And we're allowed to do that because it's actually, oh, here it is. Because of negative exponents. So a to the negative m power is 1 over a to the m power. Basically, if you have a negative. Okay, so then Elijah says, and exponent times another exponent, you add the exponents together, right? I like what you're saying, Elijah. However, you got to read the rules carefully because we have to have the same base. See how they both share a base of a to be able to add them together? Yeah, you could just, type in your calculator and get a really big number, right? But we want to figure out how we can use, it's kind of like a puzzle, right? Figure out how we can use this. We can't actually add the exponents together unless we have the same base. So one is 80 to the 1/4 power and the other is 5 to the 1/4 power. So we can't quite use this rule yet, but we could break 80 out into 5 times, what is that? My brain's not working. 5 times what gives me 80? 16. Okay. So we could make this 5 times 16 to the 1/4 power times 5 to the 1/4 power. Okay. And I'm totally running out of, oh, good. Okay. And then with our, and I don't think this rule is on here. Oh, no, it is. Power over product. Basically, I can distribute my exponent. Okay. So I can say this is also 5 to the 1/4. So what I'm doing is I'm distributing my exponent. 5 to the 1/4 times 16 to the 1/4. Sorry, I lost my pen, so I'm trying to write with a mouse. Actually, the pen broke. Okay, 5 to the 1/4. That table is so useless. It's not useless. I keep referring to it. All right, so now I have 5 to the 1/4 times 5 to the 1/4. Now I can add these exponents together because they both have a base of 5. Okay, so I'm left with 16 to the 1/4 times 5 to the 1/2. And I'm running out of room. Okay, 16 to the 1/4. Let's see if that's actually the same as writing the 4th root, right? Let's see if that's actually anything. So 16 to the 1/4 power is actually just 2, right? And I'm off my screen here. Can I scroll? Oh, good, good. 5 to the 1/2 power is the same as square root of 5. So that's how we would do number 7. There's more than one way to get there. So you could have broken 80 to the 1/4 power out first and then use the subtraction rules, and that would have worked too. It's really just kind of a puzzle of, okay, which rule can I use next? Oh, and see, the book left it as this. They left it as 2 times 5 to the 1/2 power. But that means the same thing. You guys should know that, right? 1/2 power and square root are the same. All right. Mackenzie, any requests for the next one? I think somebody else just joined. Yeah, Elijah, it makes it really fun to grade, right? For me, it's like, yeah, when you check your answers, anything combining roots. Okay. Okay, so looks like 33 through 39, which I believe is part of your assignment. 33. Yep, those are in there. 33 through 39, we got to combine some roots. So let's do that. Well, oops, that's not what I meant to do. Let's do 33 and 39. So we'll do the easy and the harder, okay? So 33, this is even if you don't like roots at all, this one I think is pretty straightforward to understand. So 3/5 cube root of 5 minus 1/5 cube root of 5. Okay, so what we want to do is we notice that we have cube root of 5, cube root of 5, right? And we can actually use, just because you've got all these crazy looking cube root, you know, all these expressions look kind of crazy, doesn't mean that we can't use our old math rules that we know. So we have two like terms here, right? So we can actually pull this out of the expression. It's like reverse distributive property, my favorite property, right? And we could rewrite this as cube root of 5, right? Because we've pulled it out of this expression. And we're left over with 3/5. All right. And in this expression, we pulled out cube root of 5 and we're left over with 1/5. And now we just need to simplify in our parentheses. So 3/5 minus 1/5 is 2/5. And then we usually write the cube root after 2/5 cube root of 5. Okay, so that's how we could do number 33. Now, when you get to number 39, it looks slightly more complicated, right? So let's go to number 39. Is this one okay, though? It's kind of if they're the same, that's really easy, right? You just pull out what they have in common. Okay, so now let's go to 39 when they're not the same. Because you see 33 and you're like, oh, no big deal. Okay, 39 is 2 the 4th root of 1,250 minus 8 the 4th root of 32. Ugh, right? Now we don't have something in common. We can't pull out the 4th root of 1,250 and 4th root of 32 because they're not the same. So we can't pull anything out. The way this is written right now, we don't have any way to combine anything. Wouldn't it be nice to be like, oh, can't combine anything, we're done. But we can do a little bit of work, right? We can try to see, divide by 8. We can try to see if 32 goes into 1,250. That's where I would start, okay? Because we can break up square roots, cube roots, 4th roots. We can break those up. So if I do 1,250 divided by 32, and I don't know if that's going to work. Nope. I don't get a perfect number there. Nope. All right. So now I need to break down 32 a little bit, right? I could break down 32 into 2 times 16, I believe. Yep. All right, so now let's see if 16 goes into 1,250. This is like a game. If you're working in a square root, you can still break down the number inside the square root, Elijah. So that's why I'm kind of looking at, okay, what do these have in common? Nope, 16 doesn't go into it. 8 doesn't go into it. I'm just trying all these different numbers because I haven't actually done this problem, so I'm just trying it out like you guys too. It's a puzzle, not a fun. I didn't say Tetris. All right, so what I'm doing, I'm not showing you on the screen. What I'm doing is I'm trying to figure out, can I break down these numbers into any smaller pieces that they have in common? And so I was looking at 32 because that's the smaller number than to figure out 1,250. So I know that 32 could be 2 times 16. It can be 4 times 8, right? And now what I'm doing is I'm saying, okay, what can 1,250? I'm trying to find something in common with both of those is basically what I'm trying to do. So I tried to divide 1,250 by 16 and that didn't work. I tried to divide it by 8 and that didn't work. I tried to divide it by 4 and that didn't work. So the only thing I can divide it by is 2. Okay, so we're going to at least try dividing 2 out of both of these and see if we come up with anything. So let me go back a little bit. So what I mean by that is that I am going to rewrite this as 2 the 4th root of 2 times 625 minus 8 times the 4th root of 2 times 16. Okay. You're like, well, that doesn't really help me. You just added more numbers in there, right? It's actually going to help us out. And so you'll see here in just a second why. So when we have 2 numbers that are inside the square root, we can break them out. So we can do the 4th root of 2 times the 4th root of 625. Okay. And we have 8 times the 4th root of 2 times the 4th root of 16. So now at least I have one thing in common that I can pull it out, right? So I can at least pull that out and have one thing in common. We actually are getting somewhere. The 4th root of the square root of 2, and I'm left over with 2 times the 4th root of 625 minus 8 times the 4th root of 16. Okay. And I know a little bit, I know from just my previous math experience that the 4th root of 16 is actually a perfect root. So if you take the 4th root of 16, you actually get 2. So this becomes 8 times 2. And if you take the 4th root of 625 to the 4th root, you get 5. So now we're just left over with the 4th root of 2 times the product of 2 times 5 minus 8 times 2. I need more room. I'm running out of room. All right, so 2 times 5 is 10 minus 16. So this is basically going to end up being -4 times the 4th root of 2. Wasn't that fun? So let's see if I have the same form as the back of the book. That's always the question. Oh, -6. Oh, that's because I can subtract well. 10 minus 16 is not -4. Should be 6. Go me. You did this one in half the space. There's other ways to get there. There's probably an easier way to get there, right? All right, who would like to see another another example from here? You guys, is that helping out? You want to see another one? Which one do you want to do? Oh, 63. All right, let's do 63. Everybody got 39. '63 looks fun. Okay, we've got x to the 4th times y to the 1/2 power plus, if I can write a plus sign, x y to the 1/4 squared. Okay, so Daniel, anywhere you're like, oh, we could start there. I think you might have, Elijah. All right, so what I would do first, yeah, because your answer was wrong. That's the worst when you come up with the wrong thing. What I would do first is I am going to get rid of my parentheses so that I can see if there's anything that I have in common. So what I mean by that is I just can't get rid of parentheses randomly, right? I have to actually apply my exponent. So I need to apply my exponent to each term in my equation. So what I mean by that is this is going to become x to the 4th to the 1/2 power times y to the 1/2 power plus, and then I'm going to apply my squared over here, x squared times y to the 1/4 squared. Okay, so when you are distributing these exponents, what you're doing is you're doing x to the 4th to the 1/2 power. So we're having a power to a power. And like Elijah said, when you have x to the 4th to the 1/2, you're going to multiply these two exponents together to get the final result. So it's going to be x to the 4th, so 4 times 1/2 is just x squared times y to the 1/2 plus x squared, and then we have 1/4 times 2, so we have y to the 2/4 power or 1/2 power. Okay, so now we actually have the same terms. Somehow that worked. X squared y to the 1/2 plus x squared y to the 1/2. And so don't forget all of your rules here, right? We're just really adding the coefficients here. So we really have 2 x squared y to the 1/2. Okay. Any questions about that? You didn't do No points if you didn't do 65. I'm just kidding. All right, so how was that? Good? You guys feeling better about chapter 6? Mackenzie, how you doing? All right, cool. All right, so what we're going to do is I just want to do a little bit of 7-1 and 7-2 because it is graphing. And then there is more to 7-1 that we'll talk about on Monday in class. So we're kind of going to do the graphing parts of those two sections today, and it really will not take very long. And then on Monday, we'll follow up because there's kind of a follow-up to 7-1. Okay, so what we're going to do is we're going to talk about exponential growth and exponential decay. So has anyone heard the term exponential growth before? Yep, we're starting chapter 7 today, Daniel. Only the graphing parts, though. Just graphing, because it's way easier to talk about graphing on the call. Okay, we're not going to go into, so this compound interest, we will go over it, but we're going to go over it on Monday. Oh, like homework wise. Yeah, compound interest. That'll be important for you guys to know as you grow up. And yeah, you might have done it in pre-algebra, Elijah. You may have. Okay, so let's go ahead and get through this. I really don't think that this particular section is going to take that long because we're graphing, and I don't think anything's going to take that long, right? It always takes longer than we think. Okay, so I have the question, have you heard of growing exponentially before? So that's a term that people like to use even like in, on the news, the growth of this, it's growing exponentially. It's kind of like growing off the charts is kind of what the general meaning for that is. But obviously in math, we have a little bit more of a definition for what that is. So yes, basically, Elijah, it's basically where instead of your x being like x to the second power or x to the third power, now your x, your variable is the exponent. So Elijah, it's in the back of your brain somewhere, you know that. So an exponential function is in the form y equals a times b to the x power, where b is a positive number, and it actually should be a positive number that's greater than 1. Okay, so yes, it's in there somewhere. So this is what an exponential function looks like. It kind of starts off really small. This is for just y equals b times x. So this is kind of the standard exponential function. So it starts off really small, and then all of a sudden the growth starts occurring, and it just takes off, and it's going to grow at a really fast pace. Okay, so we're going to just look at a couple of these graphs, and you can kind of see that. When you have growth, okay, so when you have growth, let me turn on my pen here. Okay, so what this is graphing here is y equals b to the x power. Okay, it is a growth function when b is greater than 1. Okay, so as long as this number that you're raising to a power of x is bigger than 1, then you have an exponential growth function. And there's a couple points on here that we can point out. That when you're growing, the graph rises from left to right, and it passes through these points, right? There's also something called an asymptote. So who's heard that word before in math? Kind of a weird word, right? So the asymptote, and this doesn't just apply to growth functions, this can apply to anything. The asymptote of a graph is when you have a function that is getting closer and closer and closer to a value, but never quite gets there. Okay, it kind of is like your range, right? So the range of the growth function is basically y is greater than 0. So the asymptote of this is the x-axis. It's never going to hit below the x-axis when you have a growth or decay function, but it's going to get really, really, really close. So let's do a couple of real examples here, and I'll point out what that means. And I have the notes for you printed out, and I don't know why I didn't hand them out on Monday, but I'll hand them out next Monday. Again, I don't even know if you're going to start your homework, but we're going to go over this part about compound interest. So let's just graph a couple of growth functions, and I'll just point out some interesting features, right? The test isn't due Monday. I didn't say that, did I? Homework's due Monday for chapter 6, but not the test. Okay. All right, so exponential function, growth function means that you have some number. So we're going to take 4 raised to the x power. Okay, so here is an exponential growth function. It's pretty exciting, right? It starts off, you'll see to the left, it actually says 0 because it's rounding, but it's actually never going to get down to completely 0. If you took that number way out, it's going to have some value. It's never going to actually hit 0, even though it's kind of showing it on here. It's approximating it. Okay, when you have a growth function, technically, right? When you have a growth function, it's going to hit the y-axis at 0, 1. So that's one point that it's going to hit the y-axis. The other point that always is true for exponential growth functions is that at 1, so when x equals 1, oops, I'm not even at the right spot. When x equals 1, then your y is going to be whatever your b value is. Okay, so I wish I could get that to stay on there. So when x equals 1, y is 4. So why is that? Well, my function is 4 to the first power, and 4 to the first power is just 4. So that's why when you go to 1 on your graph, when x equals 1, if I can make it go there, yeah. When x equals 1, y equals 4, which makes sense, right? X to the first power is 4. And then this also makes sense because x to the 0 power, or x is 0, so 4 to the 0 power is just 1. So that's why those 2 points are always consistent. And then after that, it's just going to grow. Okay, so that is an exponential growth function. I think I have a couple, sorry, that's not where I meant. I have a couple of them here to graph. You could do y equals, let's see what happens when we multiply 1/2 times 3x, 3 to the x power. So actually, let's do it this way. Just multiply this by 1/2. 1/2 times 4 to the x power. So this is going to modify our graph a little bit, right? Because if you think about it, now, let's just, before we even look at our graph, when x equals 0, right? That means 4 to the 0 power is 1. So that means y is going to be 1/2. Just graphing, Elijah. Except for the compound interest. Okay, when x equals 1, right? That means it's going to be 4 to the first power. 4 times 1/2 is 2. So these 2 points should be true over here if I did my math right. So when x equals 0, y should be 1/2. And when x equals 1, y should be 2. And come on, mouse. There we go. So those 2 points you should be able to graph, right? And then based off of that, then it just exponentially grows and decays off into basically the asymptote of the x-axis. It never quite crosses the x-axis, but it just gets really, really, really close. Okay, so that's what happens when you multiply by multiply a growth function. You can also add and subtract to a growth function. So let's keep our, I should have done this here. So my original was this graph, right? If I multiply by 1/2, you can see that that's not what I wanted to do. So if I multiply by 1/2, what's that? Yeah, kind of a mess, huh, Elijah? What happens if I take my original y equals x, or 4 to the x power, my original growth function, and I add 5? What do you think is going to happen if I add 5? Do you think the graph is going to shift up, down, left, or right? Elijah says up. I like it, Elijah. It's going to shift up, right? You're taking your growth function and you're adding 5. Yep. So now if I looked at my new growth function, right? My asymptote is at x equals 5. No, y equals 5, excuse me. Y equals 5. So it's never going to go lower than 5. Is it possible to do something like 2 to the 2 to the 2 as in the power has its own power? You could graph that, Elijah, but it'll probably just simplify it, right? 2 to the 2 to the 2 would just be 2 to the 4th. And then 2 to the 4th is 16. All right, so that's exponential growth. They all look like this. As long as the number that you're raising to x is greater than 1. Okay, so what happens if, what I mean by that is it could be 4, it could be 3, it could be 100. It's going to be exponential growth. In 7.2, we examine what happens if instead of 4, we put a number that is between 0 and 1. Well, let's see what happens if you actually put 1 in there. 1 is really boring, right? So that doesn't work. If you put 1 in there, get a boring graph. So there's no growth with when you have a value. They're calling this b, but it just doesn't really do anything. Okay. But when you have a number that you're raising to the x power and it's between 0 and 1, so let's take 0.5. Okay. So 0.5 is right smack in between 0 and 1. Instead of having growth functions, we have decay functions. Okay, so these are obviously different than a growth function because you're starting with a really large number and it's decaying. Anything less than 1 is a decay function, Elijah. Yep. But it has to be greater than 0, though. So if this number that you're raising to the x power is between 0 and 1, then it's decaying. And the same kind of properties apply, right? If you guys should be able to just take this red function right here, right? Y equals 1/2 x. 1/2 to the x power. Sorry, I'm being a little crazy there. Okay, so if x equals 0, anything to the 0 power is always 1. So you're always going to have that point, right? If x equals 1, then it's just going to be whatever your value is that you're raising it to. Y is going to be 1/2. So those 2 points should always be true just based on your simple knowledge of exponents. Okay, so for my red function here, when x equals 0, y equals 1. And when x equals 1, y equals 1/2. So those two could kind of make sense. The rest is in there. All right, so Elijah, you said anything less than 1 is decay, except if you try to, what happens if you try to put in -1? What does Desmos do? Let's hide these two. I don't even see it. Right? So that's why our number has to be between 0 and 1 for a decay function, and between or greater than 1 for a growth function. Yeah, -1 doesn't like it, right? You want to try -2? Looks like there's 1 point here. So you can play around with it. That's why I like Desmos, because you can, I think it's more intuitive if you kind of play with it and say, oh, what happens? You can make your graph flip over. So what if we did not actually do this? What if we did, instead of the negative inside there, what if we did, here we go, -2x. So this is different, right? Because the 2x is being negative, the negative isn't inside the function. So you can actually flip the graph by making it negative. That's like reflecting it over the y-axis, right? So there is a possibility to do that. So this is actually a growth function that's been flipped about the x-axis. So really with your homework, it's really just graphing these, but I think it's easier when you start to play with them. Like I would just encourage you to even, you know, take one of your math problems that you have to do and kind of graph it and then say, oh, what happens if I throw a negative in here? And what happens if this? And what happens if that? I know for your homework, it asks you to state the domain and range. So that's always something important to note. So like, for example, I'm on page 489. So this is 7.2, number 21. So the function is y equals 1/3. And they've got all kinds of crazy functions in here for you to explore. So I didn't even show you all of the possibilities, right? X minus 2 plus 2. Nope, I don't even know if I have that written right. Yes, I do. Plus 2. There we go. Yes, domain equals x, range equals y. Okay, so here is a decay function. This is number 21. Okay, so obviously you can graph it and look at it. It's a decaying because it starts off really high and then it kind of flattens out, right? But if we want to state what the domain and the range is, let's just do a quick review of that. So the domain is what values of x can this be? So for this again is number 21. Okay. So what do you think the domain of this is? What x's can this be? So for the domain for this, which is your x's, it's going to be all real numbers, right? Because it's obvious this way, right? It's just going to keep growing forever this way. This way as well, it can keep growing forever and ever. It's just going to be harder and harder to get those values. Like to get to x equals -10, you're going to have to go to a huge y value to get your exponential function to go out that far. And if you really don't believe me, you can sit there in your tools and you can maybe make your x-axis go to like you know, -10,000 to, you know, you can play with your play with your values there. I'm just going to kind of keep it where we're at. Okay. That's what's an option. So then now we have to talk about the range. So the range is what y values. So this one actually does have something going on because when we look at y, obviously this way it can go up forever. But when we get here, it looks like we have an asymptote where it kind of flattens off and can never get to that value. So let's do some scrolling in here to see. Okay, this is going to get closer and closer and closer and closer and closer to 2. So my range is going to be that y has to be greater than 2. You might be tempted to do greater than or equal to 2, but it actually technically is never going to hit 2, even though Desmos is telling you it's 2. It's going to get really close to 2, but it never can quite get to 2. And we can talk about in class on Monday why that actually is. That it can never quite get to 2, because there's always going to be some value. It's 2, right, plus this amount. And we can never get this amount to be quite 0. It's going to get really, really close, make it out to like 50 decimal places, but it's never going to be 0, technically. So if we wanted to do the domain and range, the domain would be all real numbers, and the range would be y is greater than 2. Okay, 10 o'clock, exactly. Nothing like pushing it to the end. So I did want to do, thank you for letting me do 7.1 and 7.2, because I think it's way easier to look at a graph on here. We will have more work in 7.1 that we'll do talking about compound interest and using exponential growth for that. So if you want to get started on your graphing homework in 7.1 and 7.2, you can. And if not, we'll still have some more time to do it next week. All right. Sorry for keeping you so long. Hope you guys have a good day. Hope you didn't check out a while ago. Thanks for coming. And I will see you guys on Monday.